So Uzay is going to tell us about the reduction, reduction algorithm.
Weight reduction algorithm and Morozov's example on the time complexity. Okay. Hello everyone. First, as a reminder, sorry that if my voice comes a little bit quiet. I'm a little bit sick today. So let's start with the definition of abstract simplicial complex. As a reminder. So abstract simplicial complex is a set of simplices, and we define simplices by a set V, a vertex set, and every subset of V is called a simplex. And we can define an abstract simplicial complex K as a set of simplices such that it should contain all the elements of the vertex set, and if something, a tau, is a subset of a simplex, and simplex is a element of K, then we should also have the tau in the set too. So this is how we define abstract simplicial complex. As an example, for instance, we have V 1, 2, 3, and we can have 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. So if you look at it, it satisfies all the conditions of being an abstract simplicial complex, and we can define a function from this vertex set to the R cube, and this set is defined as f1 goes to 1, 0, 0, f2 goes to 0, 1. So it goes to the basis of the R cube. And by doing that, we can see that these two sets are corresponding to the edges, and this corresponds to the triangle, and we can visualize this as here is 1, here is, and this is called the geometric realization of K. So this is again 1, 3, this 2, 3, and this is 1, 2. So for a given abstract simplicial complex, one can ask the question, like for instance, if we have this geometric realization of the K, 1, 2, 3, can we get this shape by adding a couple elements to it gradually? And yes, and that will be called a filtration. So at each step, we will have a nested sequence of simplicial complexes, K0, K1, Kn and K. So for instance, we can start with 3 dots at the first step, this should be K0, and then we can add an H to 1, 2. This is 1, 2, 3. Then we can add the 2, 3 H. 3, and then we can add this edge, and then we can finally add the inside. So again, this will be a filtration because every simplex that we have, every complex that we will have here will satisfy the abstract simplicial complex and set the properties, and we add couple simplices at first of 1, 2, 2, 3, 1, 3, and the inside, and we will get the final shape that we have here. So our aim is to understand how the homology changes every time we add a simplex or couple simplexes to our system. But to define the change, first I need to define the chain complex and homology. For every simplex that we can define its dimension by dimension of is k if the size of the simplex is k plus 1. So in our case, 1, 2, 3 will denote the zero simplices because their size is 1. And 1, 2, 3, these edges will define the will have the dimension 1, and this will have dimension 2. So by using that, we can define a chain complex. The chain complex is defined as Ci contains the ith dimensional, I can say ith simplices, which have the dimension I. So for instance, this will again contain vertices, this will contain edges, etc. And we have the boundary maps phi i's, which is defined as so it takes sorry, I made a mistake. No. So it takes n simplices, and this denotes removing this edge, and we will just going to sum these simplices, and this will define us a boundary map, and this will be a homomorphism. But then by these maps we can define an ith cycle and ith boundary. Ith cycle is kernel of phi I, and ith boundary is the image of phi I plus 1. So you can see that the kernel always contains this by looking at here. So we can define, since this is a normal subgroup, we can define the HI homology of K, which is this is denoted Zi, this is denoted Bi, just the quotient group of Zi divided by Bi. So this means that this homology has the equivalence classes such that something is a cycle but not a boundary. So looking at here, by using this idea, we can say that, so here we don't have any C1 class, so everything in C0 should be a homology class. So here we have homology classes H0, 1, 2, 3. But as soon as we add 1, 2 here, we now have a C1 element here, and its boundary is 2 minus 1. So when we define the quotient group for H0, now everything, we take the quotient group by this. So since 1 times, so since 1 times this is 2, so 1 plus this is 2, this means that we have an element, another element here, such that it is, they are connected by this element here. So this means that 1 and 2 now have the same homology class. So when we get here, we don't have these two classes, but just one of them. So by choice, I say we kill the 3. Sorry, we kill the 2. By same logic, this, when we add this, now 2 and 3 has the same homology classes. But since 1 and 2 has the same homology classes, this means that 1, 3 now has the same homology classes. So now H0 just only have one element in it. So, but when we add this, now we don't kill anything, but what we do is that we get a cycle. Because if you look at the boundary map of 1, 2 plus 1, 3 plus 2, 3, that will be 2 minus 1 plus 3. The direction is important. 3. 1 minus 3. And so since everything cancels each other, this will be equal to 0. So now for the boundary map, we have something on the kernel. So we have created a cycle for H1. So now H1 is this cycle right here. 1, 2 times 3, 1 plus 2, 3. And H0 is just 1. But when we add this 1 to 3 simplex, now the boundary of this is 2, 3 plus, sorry, minus 1, 3 plus 1, 2. By this minus property, you can change the order of here. And you can see that now when we add 1 to 3, the cycle, now this simplex has the boundary, which is the cycle. So this means that we killed H1 class too. So this is the map of how the homology changes, but we can visualize it better by putting it into a barcode. So barcode. Now in barcode, at the bottom, we put the simplicial nested sequence of simplicial complexes, K0, K1, K2, K3, and K4. And we look at how the homology classes change by looking at this barcode by, for instance, we have the homology class of 1, which is always present in all the homology classes, all the homologies of the simplicial complexes. So this goes to infinity. But when we look at the 2, now 2 started at k0, but died in k1 because when we had the 1, 2 simplex, we have killed the homology class of 2. So we have this. Again for 3, we have it at the start, but it is killed at k2 when we had the 2, 3 simplex. And lastly, we have the homology class of A, which denotes this. Sorry. 3. And which borns at k3 and dies at k4 by adding 1 to 3 simplex. These are H0 homologies. This is H1 homology change. So this shape is called a barcode, where the beginning point denotes the birth of the homology and the end point denotes the death of an homology. So we can also put this into something called persistent diagram. So here we have the birth of the homology and we have the death of the homology. We have x equal y line here. So for instance, for the 1, the birth is 0 and the death is at infinity, so we denote it by putting at the top of this deadline. Now for 2 started at k0 and died at k1, so we denote it by putting 2 into the 0, 1 point, which is here. Similarly for 3, we have 0, 3, and for k this barcode, we have a birth at the 3 and that at the 4, so 3 here. And this is the, I should denote it by a different color. Here the blue ones are H1 homologies and the black ones are H0 homologies. So by looking at the barcode, we can say a couple of things. For instance, if we have a long H1 bar here, that will imply that there is a cycle like this that is persistent for a very, very long time. So that will mean that maybe our shape can have a huge hole in it, like this shape. So again, we want to get this barcode more in an efficient way, because looking at each time how the homology changes will be very costly. So they, I think Kerber in 2005 developed an algorithm for that, and that's the matrix reduction algorithm. Now, in matrix reduction algorithm, first we have a given filtration, K0, K1, Kn, and then we put the simplices in the order that they occur on the filtration. For instance, in this example, the first one that occurs are 1, 2, 3. So 1, 2, 3. And the second one that occurs is 1, 2, then 2, 3, and 1, 3. 1, 2, 2, 3, and 1, 3. And the last one that occurs is 1, 2, 3. And we put the empty set here just for the definition. So we put them in the order that we put at the vertices, in the vertical order too. So we have 1, 2, we have 2, 3, we have 1, 3, and this is a matrix that contains of 0 and 1s. Actually, it is a matrix in Z2, such that we have the 1 value if for this column, for example, the boundary is, how can I say that? So if something is the boundary of this column, we put 1. If it is not, we put 0. For example, for 1, the boundary of 1 is empty set. So we put 1. But for 1, 2, the boundary of 1, 2 is 1 and 2. So we put 1 and 1 here. So for 2, 3, the boundary of 2, 3 is 2 and 3. So we put 1 and 1 here. For 1, 3, the boundary is 1 and 3. So we put 1 and 3 here. And for 1, 2, 3, the boundary is 1, 2, 2, 3, and 1, 2, 3. Sorry, 1, 3. So we have 1, 1. So everything else in this matrix is 0. And we are working on Z2. So for this matrix, we define something called log of a column, log of a simplex, which is just the one value at the bottom. So for instance, for this column, the log is this. For this one, this is and this. For 1, 2, the log is 2. For 2, 3, the log is 3. Again, this for 3. And for this, it is 1, 3. So first, we start from the left and we do the operation by if these two columns have the same laws. For instance, at this case, we add the one at the left to the right. So we add this to this. So, but when we add this to this, since we work at Z2, this will be a 0 column. Again, by similar algorithm, we go to right and we see that, okay, 3 has the same law as 1. So we add 1 to 3. So this again will be 0. For 1, 2, the law has not been taken before. So we don't do any operation for 1, 2. For 2, 3, the law of it is 3, which has not been taken before. So we don't do any operation. But when we get to 1, 3, since 2, 3 has taken 1, we add this to this. So we get here 0 and here 1. And our new law is 2. But since that 2 has been taken before by 1, 2, we add 1, 2 to this. And this will be a 0 column at the end. And we don't do any operation for this because the law of 1, 3 has not been taken before. If you look closely, you will see that this means that 1 is killed by empty set, which means it is not killed by anything, so it goes to infinity. But when we see that 2 is killed by adding 1, 2, you can see it here, and 2, 3, 3 is killed by 2, 3, which is here, and you see that 1, 3, the cycle that we created by adding this 1, 3 is killed by 1, 2, 3. So this gives us the barcode of the filtration by just doing some matrix operations. What's the benefit of it? The benefit of it is that we can code it. A computer can understand it, which we already did with Ergin. So for a given filtration, we can find the laws and the pairs easily by doing some operations. There are also many clearance techniques for the columns, but the thing that I want to emphasize here is when we have 0 columns, you can see that these are also the columns, also the values which are matched with the laws. So actually, when we have a 0 column, this indicates a birth. For any other columns, if something is a law of something, this emphasize that. So if you want to look at the time complexity of this matrix algorithm, you can see that. Mhm.
The barcodes are constantly equivalent to each other up to what kind of equivalent?
Can I get the question?
Like here,
Mhm.
it looks like you're getting different barcodes in terms of lengths, in terms of starting points.
It's by looking at this matrix algorithm, we cannot actually we can say like when it borns or die if we know, for instance, and which filtration 1, 2 occurs.
After this algorithm, what
Mhm.
kind of barcode do you draw?
After this algorithm, I don't draw the barcode. I can say that I can say the intervals, not the barcode, but intervals.
This is that because you open the filtration 1, 2, 3,
Mhm.
1, 2, 3, like your barcodes are longer.
Mhm.
It says each figure, once you do the matrix algorithm, those simplices that you put in different places, they match to the same real number. So the barcodes using those filtration.
Mhm.
So in other words, this 1, 2, 3, that they all have the same filtration level. So once you find out that there will be a line between starts with filtration 1. Go back to the filtration. Makes the barcodes exactly same.
So if you want to look at the time complexity of this, assume that we have n many here. So for instance, this column, first we should check the low of it, which I already deleted, but first we should check the low of it. But if it's a very long column, that means that finding a low takes O(n) time complexity, because we check that whether it is 0 or 1, and then if we have 1, we check whether something below that is 1. So it has time complexity of O(n). And then we should also check how many columns are there for the low. So that adds a time complexity. But if something has the same low, for instance, for 1, 3, this means that we need to add to this, but the complexity of this depends on the number of ones on the column. So if we have n many ones on the column, that means that we need to change n many entries of the column. So that adds a time complexity O(n), and we need to do this for O(n) many columns. So the time complexity becomes O(n) cube for this algorithm. So since this matrix reduction algorithm has time complexity O(n) cube, one can ask that, okay, like from here it can be seen that why it should have time complexity O(n) cube, but can we give an example for it? And in 2005, Morozov gave an example, and I'm going to talk about that in detail. Is there any question so far? No? Okay. So Morozov first describes this as he describes the shape of this example. It's the Y cube. First, he starts by this saying this sentence. We describe the space as well as the ordering of the simplicities. Let n be and so it is a floor function of capital N plus 29 over 7, and V is the floor function of n minus 1 over 2. So he starts with a big ABC. And he starts adding some vertices inside of this this triangle by this fashion. We add V many vertices. So he adds V many vertices in this manner. So he put the first matrices, the first vertices near the middle of BC. So for instance, somewhere around here. And then he puts the second vertices near the, sorry, should we see? He put the second vertices near the middle of AV1, so somewhere around here. He puts the third one near the middle of BV1. That's V3. And then he puts the fourth one near the middle of AV2, which is around here. V4. The fifth one near the BV3. Sixth one near the middle of V2, V1. And the seventh one near the middle of V1, V3. So the way I interpret it is like first putting something in the middle, and then putting the vertices by first putting it into left and then right. For instance, V1, V2, V3, V4, V5, V6, V7. So by this manner, he gave the visualization of it by V is equal to 7. But if we want to add more vertices to this, we first put the 8th one here, the 9th one here, the 10th one here, 11th, 12th, 13th, 14th, and 15th. That's how he put it, all the vertices inside of it. So we can put V many vertices in this manner, and then we can connect them. Yes. He also denotes this triangles inside the triangle as base triangles. So the denotes, this is denotes. Can you read it, by the way? Okay. Base triangle. Base. And the notion of it is done by looking at the top vertices here. So if we have the top vertices V2 here, so this is the second triangle. So this is the third triangle, fourth, fifth, sixth, and seventh. At the top of it, up to this point we have two dimensions, yes. So imagine this shape here as a triangle, Now we put something above it, like a plane, and we put n-1 many fin vertices. So we put n-1 many vertices here, and we start connecting it by these edges. So as an example, for example, so to visualize it, for instance, for V1, we have the shape like this, which is like a fin, like this. I'm not going to draw here because it will just complicate the picture, but just remember that we have n-1 many edges like this, which is put above every edge here. So we have one edge here, we have one edge here, we have one edge here. And then he starts also starting denoting these edges by in terms of n. First he puts n here. This is the nth edge. This is the n-1 edge. Sorry, pardon. Yanlış oldu. This is the nth edge. This is the n-1 edge. This is the n-2 edge. Again, by putting into right, left, that kind of fashion. n-3, n-4, n-5, n-6, 8, n-9, n-10, n-11, n-13. And we denote the AB edge as 1. So in our example, the n is equal to 15. Because when you put 15, you will see that this will become 2, 3, 4, 5, and this edge between will be 15, and we will have 1 here. So he also denotes this, and these are fin triangles. These did I forget anything? No. We also put, if I say minus k, that will mean that since this fin triangle have 2 other edges, except for this one, we will denote one of them with minus k, and the other with minus k star. So when I say minus k, it will be a fin edge, one of the fin edges. It doesn't matter which one, just the one of them. So how do we put the numbers to the fin edges? And that is done by if it is how can I say, the index of this plus the index of fin edges should always be n plus 1. So here we will have the first fin triangle, 1 plus n is n plus 1. So here we put the second one, since 2 plus n minus 1 is 2. And then here we will have the third one, the fourth one, etc. So we will have we will have n minus 1 fin triangles. We don't put at the AB edge, only the edges inside the triangle. So then he gives the filtration for this, the order of filtration to this shape, which is first the vertices, and then edges with vertex C. Then he put just one of the fin edges. I will denote them by minus k. Let me denote by red. And at the fourth step, he starts putting the other fin edge here, which will be. And sorry, the order here is important. So we will start by n minus 1 minus n minus 2. And it will go until minus 1. Here again, it will start with minus n minus 1. And it will go until minus 1. So at the fifth step, he starts putting this inside edges. So say 1, 2, n. At the sixth step, he starts putting the triangles, the inside of the triangles. Like 1, 2, and V. Then he starts putting the triangles here that has the vertex C. I will denote them as C triangles. And at the last step, he puts the inside of the fin edges. Sorry, fin triangles, which will be minus 1. That's the order of the filtration, and our claim, or Morozov's claim, is the time complexity of the example is O(n)3. That's the claim, and now I'm going to prove why the time complexity is O(n)3. Maybe I should do it. First, I want to start with the fact that since O(n) is a kind of linear function of capital N, and V is kind of like a linear function of N, we can actually work on the small n or small v as well. So when this capital N is done to put both v and n into the parameter n, but we can also work it on O(n) and OV. Then we can prove that it's actually O(n)3 here. So first, it will be. I'm not going to draw. Proof of our claim. So first, we add the vertices which creates, at the first step we create H0 homologies by adding the vertices. So there's nothing to do there. We just like create each H0 homology for each vertex. But at the second step, when we add the edges with vertex C, for instance, this, let me give some order. V1, VV, F1. These are the fin edges, sorry, fin vertices. These are the base triangle. Triangle vertices. And these are CAB. So, for instance, when we add the CA, now both A and C has the same homology class in terms of H0. So we can kill the A homology by adding the CA. So we have the pair A with CA. So because the CA's low is A. If you look at the if you look at the matrix reduction, you will see that since A occurs later than C, this is a choice by the way, since A occurs later than C, when we add the CA, now the law of CA is A. Similarly, law of CB will be B. For the V1s, each VI will be the law of CBI, and then nothing after to do here. So here we don't do any operation, we just look at the matrix and see that the laws are unique and they pair by this pairing. But when we add this -1 edges, we see that now this is the thing that kills the fin vertices, because one edges, for instance, VI, which occurs earlier than the fin edges, and since the law of this edge is either the VI vertices or the fin vertices, we can see that when we add this minus k stars, what we do is we pair them with the kth fin. So there's nothing to do as an operation wise here. But when we add the fourth one, now when we add the fourth one, we let me just, when we add the other edge, we see that we actually create a cycle because we already have this edge here. We now have this edge, and this edge. So actually, what we do is we have created a cycle like this, at this, like this shape. So how do we get the cycle? First, since the law of this edge is say phi k and some vertices, we first add minus k star to k star, and then adding two C vertex edges. I don't know which ones, Ci and Cj, I will say. The boundary of this is, now this is a cycle. So that means that adding every minus k, adding the minus k here resulted with an birth of an homology. So okay, I will birth of an homology. So at this step, we add three edges to the we put three edges to the one edge, and since we have on many of them, the time complexity of here is on. And as I said, at the end, the minus k will result in a birth of an homology, which we will seek which complex will kill the homology that minus k started. So at the CICJs are two of them. I don't know which one, but two of them. It can be CA, CB, or CVI, CVJ. Like, did you get the shape? Like why they create a cycle? Or I can explain it better.
Would be nice to
okay.
indicate maybe on the.
Okay. So assume that we have an edge that goes into the shape like this.
Yeah.
So before adding one of these edges, we had this edge, and this edge in terms of the filtration. But as soon as when we add this, now this creates the cycle. Yeah. That's why it's resulted in a birth of an homology. So at the fifth step, now you can see that they also create an homology too, because we have this edge here, and we also have all the C edges here, the edges with vertex C. So when we look at this, we also see that, for example, for this edge, this also again create the cycle here. For every NH, we have created a cycle by adding two. Let me just say, let me see. I will say one, but you can get again cycle. So every NH will also create a cycle when we add them. So they will remark as a word of an homology. So at the sixth step, the things get a little bit tricky. Okay, I can put them here. Now, when we look at the boundary of 1, the boundary of 1 is n minus 1, and 1. So looking at the filtration order, the low of this triangle is n, because n is the latest part of the triangle that occurs. So 1 is directly paired with n. Again, we expect that because every edge here results in a birth of an homology, and at the sixth step, we kill those homologies. But now adding 2, sorry, pardon, şunların indekslerini yanlış yapmışım da. It's often confusing to put the numbers to them. Six, n minus 7, n minus 8, n minus 9, n minus 10, n minus 11, n minus 12, n minus 13. Sorry about that. So when we add the 2, we see that the low of it is n, because in the boundary we have n minus 2, n minus 4, and n. And since n is the last one that occurred, the low of it is n. But the low n has already taken by 1. So we add 1 to 2 because of this rule. And at the end, we see that 1, 2 is this shape right here. This, let me do. This. And the low of it is n minus 1, because n minus 1 is the latest that occurred in the filtration. So when we look at the tree, we will see that the low of it is n minus 1, which has already been taken before by 1 plus 2. So we need to add 1 plus 2 to 3. But when we add that, now the low of 3 is n minus 2. And this will go on until we add the v vertices, which will pair with n minus v plus 1. Did you get this part? This is the most important part of the filtration. Now, looking at these things, you will see that the number of ones on every column is depending of the number of n's. So the length of, for instance, 1 plus is depending of on. So we will have on many ones in this part here. So again, when we had the C triangles, their filtration is not given by Morozov. Filtration, not the order of their occurrence is not given by Morozov, because in every, for instance, we say 1, 2, 3, 4. The order is not important. Order indexing is not important because at the end they will all pair with one of these edges, because these two edges came before the NH, so these will automatically be paired with this ones. So at the 7th step, again the CVIs will be paired with some edges from here. Again, their time complexity is ON, so it doesn't affect ON cube neither. But at the last step, now, just by looking at this shape, when we add this, the inside of the triangle, the minus k star is already paired at this step, so it cannot pair with this. The bottom edge is already paired by either CVIs, or either with the base triangles. So the only option that this inside will be paired will be with minus k. But to get there, first it needs to remove everything that comes before it, like this part. There's my filtration. The minus k is here. The minus k is here. Our triangle minus k is here. To get there, first we need to eliminate all the other possible laws of this. Now, the first law of this is if we take the -1 case, for example. Now, the law of -1 is, sorry, the law of -1 is n. But to get rid of this n, first we need to add the 1 to it. But when we add 1, the boundaries of 1 is n-1 and 1. So the new law, according to this filtration, will be n-1. But n-1 law has already been taken by this, so we need to add this to this. 1 plus 1 plus 1 plus 2. Now, when we do this, the new law will be n-2, which will again be not enough because the n-1 is n-2 has taken before. So now we need to add this to this. So by this algorithm, we need to add all these triangles to this, including the where is the 7th one? Okay, including all the C triangles here. So again, at the end, we will have a long series of this will move on. After doing all these steps, it will be matched with minus k. Sorry, it will be matched with the -1 edge. So the thing that is remarkable here is that, recall that I said that every column has OM many ones here. So we add, so the time complexity of each is On, but we have On many columns like this to add to here because we need to first eliminate from every edge to N to 1. And then, since one of them takes the time complexity of -1 is On square, but since we have On many thin triangles and -1 many, so computing all of them like this logic will result in On cube time complexity. So the claim of the Morozov is real. The algorithm really works at On cube time complexity here. Is there any question?
What is the essential feature about this kind of?
The details of the space is not given in the article, like explicitly.
What makes it? What fits this? What saturates this complexity in this space?
The things that saturate this complex is again the law of this triangle here has been taken before. So to eliminate that, we need to add a lot. We need to do a lot of operations, or many operations, which all have OM many ones. And since we have OM many triangles like that, the time complexity is OM cube. So the magic of the Morozov comes from this long series of addings, OM many columns.
Okay, maybe I should ask maybe more basic ways of using the pattern of adding these triangles.
Matter.
Are there different ways of constructing spacing, like Morozov?
Me and Ergin just constructed one example, and I will explain that.
So what is the common feature?
The common feature is when we do that too, the common feature is these edges here. For instance, when you look at the 1 and 2, they have the same law. So we need to add something to something here. In our example too, we need to eliminate a lot of we need to do a lot of operations to uniquely pair them, and to get the latest pairing, we need to first eliminate all the possible values here. That's like, if I tell my example, you will understand better probably. The time complexity comes from this zigzag thing. We always put at like for 1, 2, 3, 4, 5, 6, 7, that kind of pattern. Now, the Morozov's example, which is given in 2005, I forgot. Is, in my opinion, a little bit complicated example to give, although the result is again ON cube. But me and Ergin has constructed a new example using this idea, and now I'm going to talk about it. The important remark of this Morozov example is that we already knew that the time complexity of such an algorithm, before this matrix algorithm, there was an algorithm called pairing algorithm, which is what I did here, very similar, by Adasbrunner in 2002. The article is written in the idea of Adasbrunner's pairing algorithm. The remark here is that first, it has been known that the upper limit is ON cube, but can we get the ON cube? There were no prior examples to Morozov before Morozov. So that's why this shows that there's actually an filtration and an example that gives us this upper time complexity.
Oh, you said you're choosing the order on the words.
Mm-hmm.
You add the extra part to the algorithm. Like once you choose the order on the vertices, rearrange all the edges, everything, higher simplices according to the order you selected on the vertices. Like for example, V1A edge will not be n because V1A comes very beginning of the order, so it can't be n, it can't come at the end.
So if you make all these compatible to the order of the vertices, then
will it
the algorithm
reduce
works
the? You said I will reduce the time complexity.
well,
That's what.
yeah, will it reduce? Like if all the higher simplices are compatible with the order of the vertices. So now there's no left right this time because everything is compatible to the
Hmm.
will it reduce the time?
I haven't thought about it really, so I don't have any clear answer to that. But the comment that I can give is like if at the end it will not reduce anything that we have done on the 8th step, so probably not.
No, but the order will change, right? I mean, all the orders in the other filtration will change. For example, n will be the first one, one will be the last one. Once you order everything compatible with vertices.
But will it define a simplicial complex? So will it define a simplicial complex? That's the ordering?
I'm just changing the orders.
It could be. I haven't thought about it too.
This is order.
Yeah, this is a very yeah.
In applications, I guess most of the reduce complex coming from data runs in much smaller. So even like there's one paper says it's close to linear, but it's random. As you taking data and close to.
I think the worst case that they have found is O and omega, where omega is like 2.3 something. In the general examples, this is a very like neatly, yeah, it's a very neatly written like example to achieve the ON cube. So, how much? Okay, I have like 20 minutes or so, so I can give my own example. First, we start with a triangle at the middle, and then we start adding triangles to its right and left, like this. So at one point, biraz daha sağa yazayım. We had n minus 1 many triangles for a given n, and then we add an extra triangle here that has vertex C. And then we denote the top and bottom ones as we want, but I will denote them as 1 bar, 2 bar, 8 bar. And then we will continue here, I plus 1, J. It will go on like this. We denote them by double. Tırnak işareti. So, and then we will denote here by 0 and J plus 1. So again, the indexing will be similar to Morozov. First, we will put n here. This will be index n. This will be n minus 1, n minus 2, n minus 3, so on. So we first put at the middle n, and then we put at the right n minus 1, n minus 2, n minus 3, n minus 4. Go on. This goes on like this. And again, this will be 1, this will be 2, 3, 4. So this will go on like this. The last one will be n minus 1, and this one will be n. Since we added n minus 1 triangles here. So and we also have thin triangles above every edge, like that, like we had on this example. But I'm not going to draw all of them. I'm just going to draw one of them. But every edge here will have a thin triangle attached to it. So the filtration order is, again, the vertices, which will be C. And then you can denote here however you want. You can say V1, V2, V3. I would say Vj. And then we will have, this will be, sorry, 1, I think. Here we have 2. So we will also have, again, n minus 1. I think n many thin triangles. So we add n many thin vertices. Then, just like Morozov, we start adding these edges at the top and bottom. These are included. 0 bar, 1 bar, 3 bar, 3 bar, 2, okay. And then we will start adding again just the one edge of the triangles, and then we will add the other edge of the triangle, and then we start adding the triangles inside by 1, 2, n. Sorry. Yeah, again, first we will put 1, 2, n edges here, and then we put the triangles. 2, n. And at the last we will put the inside of the edges. -1. This again works at O(n) cube by similar argument, because at this point the vertices will be same argument. All of them will create an H0 homology, which are bird. When we add this here, this will again kill one of the vertices here. So this will kill the vertices inside, except by choice C. By adding one of these edges again by the same argument, it will kill the thin vertices. At this point, similar to Morozov, since we have one edge here and the other edge here, and we also have all the other edges here, this again creates a cycle. You can see it creates a cycle here. So this will result in a bird of an homology. And again, it will be killed when we add the inside of it, which is at the last step. So again, when we add the edges inside of it, similarly, they again create homologies, because we can go all the way up to this, and then we can get this cycle here. So again, they will result in a bird of an homology. At this step, again, we will see that the law of 1 is n, because the double edge is added at this step, the n's are added at this step, so these are later. and then n minus 1, and n is the later one. So the law of this will be n. But 2, sorry, this will be 2. Yine karıştırdım. Şurada 4. Now the law of 2 is again n. So we need to add 1 to 2 to get this shape, this parallelogram kind of shape. And this has log n minus 1. Again, when we add 3, this will have log n minus 1. To reduce that, we need to add 1, 2 to that. So this will result in log of 1 to 3 being n minus 2. And it will go on until the n triangle 1 plus n will be paired with the 1 edge. So at the last step, again, when we add this inside of them, we notice that first we need to remove all the edges that they are on. So for instance, for the -1 case, we first need to the simplex that has log n, which is 1. But when we add 1, again, this will have log n minus 1. To remove that, we need to add 1, 2. And again, when we add this, the law of will be n minus 2. And to remove that, we need to add 1. And go on, and so on. So when we do this, we have on many columns, which have, again, on many ones in them, because you can see that the ones are actually the number of edges that they contain, and they get bigger and bigger every time we add them. So this will have time complexity on square when at the end. And since we have, again, n many thin edges, this will again be on cube for every. Then we complete the whole algorithm. The benefit of this is, compared to Morozov, first, now we don't need these triangles right here, which again in the paper is not detailedly explained, because now naturally all the triangles are now paired with the edges. And another application is here it is harder to tell whether it is coming from a metric space or not. But from this example, I think telling whether it's coming from a metric space or not is easier to tell, which I don't know. Me and Ergun are just still thinking about it. We hope that we can find the metric space that comes from it. Okay, that was all that I want to talk about today. Thank you for listening. Is there any question? Is there any question? Yes. Okay.
The common feature is this
Mm-hmm.
right in there.
Mm-hmm.
This figure more or less looks the middle part of that.
Mm-hmm. Yes, kind
How
of.
do you get the intuition to construct it?
First,
Hidden in that space.
yeah, we first start with the idea of like putting all of them inside the triangle will probably result at like a collapse or something. So we want something more free that we can add, or we can tell computer to generate better than Morozov's example. So that's where the idea comes from, the left and right adding as much as we want.
You have a code where you can generate these types.
We don't have any code, but I believe that this is easier to code than this.
To write the simplicial complexes, like input the simplicial complex to the program.
Yeah.
To make this complex. But when we try to do that, we realize that these edges and vertices are very difficult to explain. There is no pattern. We go right, left, right, left. But in terms of the numbers, if you say your vertex set is 1 to 10, how do you explain each edge in terms of those numbers? You have to explain it simplex. In this example, it's easier to explain. You can write the code for n equals 5, I mean, these are like example 6, 7, 8 by changing the simplicity. It's a more regular pattern. That's why we try to write something simpler than different names. And the question came up: is this example they come actually from the data? Data or connected analytic space will give you this result of this Wafers, Ripser, check complex. Wafers, Ripser is not possible because edges comes much later. Triangles comes much later than edges are ever. So I think it's not going to be Ripser. But maybe it will become a check. Certain set of points you can choose. For those kind of questions also, the simpler example you decide. You couldn't decide yet, but that you can decide if there's a set of points. But you can actually apply the chain construction. I don't know if that's possible.
Are there other classes of examples?
As far as most of the articles refer to the Morozov as an example, no other example.
I mean, yeah, it's a very good question. We found something for the simplicial complex. Huh? There is a theory, there's a couple of papers we were discussing last week, right? But the ones that comes from graphs, the graphs networks, and they're weighted, which is a number, they give you filtered graphs. And those good complexes of these graphs gives you simplicial complexes. They will give you filters. And there's an inequality for the weights. For such a weighted graph, to give you simplicial complex to come from. So there is some applications in biology.
They are looking at how similar the DNA parts are, and then putting it into a distance matrix, they will decide on how it will come from a tree by doing some algorithm. So, if there are any other questions, then I thank you again. Thank you.